4a, the question is f equals is that x bar or double bar? It looks like x bar. Y plus y bar z bar plus x, y, and z. And the question, show a truth table of the following function. Now I'm looking at my variables. I see x, y, and z. That's all I see. So I have three inputs. I'll use this box for x. I'll use this for y. I'll use this for z. And I'll do this, my output f, the function f. Now let's list all the combinations for x, y, and z. It could be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Let me show you quickly. How do you know? How do you make that table quickly? How many inputs you have? 3. What's 2 to the third?
8.
You will have 8 different combinations. If you have 4 inputs, I don't need them yet. You can put them at the end of the class, you know. What's 2 to the fourth if you have 4 inputs? 2 to the fourth is what? 16. So you're going to have 8 boxes. Let's count, see if we have 8. 1, 2, 3, 4, 5, 6, 7, 8, right? A quick way to write that combination without having to think about it. Go the first one. 0, 1, 0, 1, 0, 1, 0, 1. The first group. Every other one. See how it changes? 0 to 1, 0, 1, 0, 1, 0, 1. The next group. 2 zeros, 2 ones. 0, 0, 1, 1, 0, 0, 1, 1. Every 2. The next group, every what? 4. 4 zeros, 4 ones. If I had another group, it would be what? 8 zeros, 8 ones. 16 zeros, 16 ones. 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth. This one says f is going to be 1 when what? Let's look at this one. When x is what? 0 and y is 1. Why? Because you're looking at that and it's an AND gate. You have an AND gate, but you have x being complemented. There's x naught. There's a naught going to it, and there's a y. That's a multiplication. So when x is 0, when you complement that, what are you going to have? 1 here and a 1. So you will have a value of 1 when this is 0 and this is 1. When you put 0 for x and 1 for y, you complement the 0, that becomes a 1 here. What is 1 and 1? 1. That's this gate. So look at my chart. Where's x is 0, y is 1? Is that these two? I got a 1 here, and I got a 1 here. When x is 0, y is 1. The second one, you're going to have a value of 1 when that's an AND gate, and the AND gate will have a value of 1. Notice this is y bar, so you have y and z. You're going to have a value of 1 when both of these guys are zeros. Why? When you complement the 0, what do you have? A 1. When you complement 0, you have a 1. What is 1 and 1? 1. So let's find out what is y is 0 and z is 0, and let's put the 1 there. There's a 1 here, and there's a 1 here.
So when there's bracket above it equals 0 automatically?
You need that to be, because that's an AND gate.
That's a property, correct? From last class.
What do you mean? That's a complement. So when this is 0, complement that, that's a 1. Remember, that's a multiplication is an AND gate. For an AND gate to be a value of 1, that means the result of this has to be 1, and this has to be 1. That means before I get to the complement, these guys have to be zeros. Because when you complement each one of them, the 0 becomes a 1. And the last one, that's an AND gate. And for that AND gate to be a 1, you need X to be 1, Y to be 1, and Z to be 1. That's when you have a 1. When you have a 1, 1, and 1. That's the only way this gate will be a 1. So that's the last case. The rest of them will be zeros. And that's what the truth table for F. If you go and build this, that's actually an OR gate here.
We can't see the side, by the way, on the screen. We can't see the far left or there.
That's an OR gate because it says this or this or this. So this will be a 1 when this is 1, or this is 1, or this is 1. If this is 1, 1 plus anything is 1. If this is 1, 1 plus anything is 1. If this is 1, 1 plus anything is 1. F will be 1 if either one of these guys is 1. Let me look at the next one, B. I know it wasn't part of the homework. And it says G equals what? XY plus X bar plus Z Y plus Z bar. The other way of doing it, if you don't like what I did here, let me go back to this one. If you don't like what I did here, go back and break it down to 3 pieces. Go, let me find where's X bar and Y. X bar and Y. What is 0? Complement that. That's 1 and 0, that's 0. Complement that, that's 1. 1 and 0, that's 0. Complement this, 1 and 1, that's 1. Complement this, 1 and 1, that's 1. Complement this, 0 and 0, that's 0. 0 and 0, that's 0. 0 and 1, that's 0. 0 and 1, that's 0. That's the answer to this piece alone. Let's look at Y bar, Z bar. Let's see what that is. Both of these guys have to be 0 for the answer to be a 1. That's a 1. That's a 0. That's a 0. That's a 0. That's a 1. That's a 0. That's a 0. That's a 0. They both have to be zeros for the answer to be 1. And the last one, X, Y, and Z. 3 things. To be a 1, all 3 have to be 1. So the last one, the rest of them are zeros. Now this one says what? Take the output of this, the output of this, the output of that, OR them together. When you OR them together, let me OR these guys. What is 0 or 1 or 0? 1. What's 0 or 0 or 0? 0. 1, 0, 0, that's a 1. 1, 0, 0, that's a 1. It's an OR gate. 0, 1, 0. 1. 0, 0, 0. 0. 0, 0, 0, 0, 0, 0, 1, 1. Is that the same thing as this one? So you could broke it down to find the answer to each piece and add them. Maybe I'll do that for the next example here, because that'll be a challenging one. Again, how many inputs do I have? X, Y, and Z, right? I get 3. Here's the combination. 0, 1, 0, 1, 0, 1, 0, 1. 0, 0, 1, 1. 0, 0, 1, 1. 4 zeros. 1, 2, 3, 4. 4 ones. 1, 2, 3, 4.
Please slide the page up.
Yep. Now let me look at the output here. Let me do column for this one. X and Y. Just X and Y. That's an AND gate. You will have a value of 1 for this when both are 1. X and Y. When they're both 1s, you'll have a 1. Otherwise, you're going to have a 0. That's this gate. Let's look at this one. X bar plus Z. Plus. That's an OR gate. You're going to have a value of 1 OR gate if Z is 1. Let's find out where Z is 1. As long as one of them is 1. This one, this one, this one, this one. Or, that's an OR, when X is 0. That's the first one. I already have a 1 here. That's this one. And that's it. So this one will, that's an OR gate, will be a 1 when either this one is 1 or that one is 0. Let's look at this. Y plus Z bar. This is an OR gate. You're going to have a value of 1 when Y is 1. Where is Y is 1? That's 0. Dropped a little bit there. I'm going to line them up here. So 0, 0. There's Y is 1 right here. And Y is 1 right here. Or when Z is 0. When Z is 0, that's a 1. 0, 1, 0, 1, 0, 1, 0. So that's when you're going to be 1. The next one, this one says take this and this. Take this column and this column, and them together. Let's AND them. Let's make sure I stay on the same line. I keep dipping down. What is 1 and 1? That's an AND. 1. What's 1 and 0? 0. 1 and 1. 1. 1 and 1. 1. 0 and 1. 0. 1 and 0. 0. 0 and 1. 0. 1 and 1 is 1. So this is the answer to this. I have the answer to this. The last step says what? OR them. Take this column, OR it with this. OR it. 0 or 1. 1. 0 or 0. 0. 0 or 1 is 1. 0 or 1 is 1. 0 or 0. 0. 0 or 0. 0. 1 or 0. 1. 1 or 1. 1. And that's what G is going to be. So you can use the truth table to get the answer for that function. Any other questions?
8A.
8A. 8A. Reduce the following. Okay. Let me try 8A. What do we have? X bar Z plus X Y bar Z plus X Y Z. Now I'm looking at these two. See these two? What do you notice about them? They have they have what? XZ as common, right? So if I take XZ out, what's left? Y bar plus Y. What is y bar plus y? 1. An AND gate, when this is 1, xz and 1 is whatever xz is.
You would be able to use the other one.
I can simplify it more. What do they have in common?
They have Z.
Take the z out. What's left? X bar plus x. What's x bar plus x? 1. So here's what we're telling you. If you were building this in the lab, you will need a NOT gate for the x. You will need an AND gate here to get xz. That's this part here. You will need an x here. You'll need a y going through another NOT gate. And you will need a z. Another AND gate. And this one x, y, z. Then you're going to take the result of these and do what with them? Or them together. So you will have 3 chips on that board. 3 of them. Well, the reason I said 3 because I can take a 3 input AND gate here because they come on multiple 3 on one board. And I make that a 1. If I put a 1 on it, this one stays the same. So this is 1 gate, 2, and 3. There's a chip that has 3 input AND gates on it. So I can use 1 chip for these.
What about the OR gates?
I need 1 for the OR gate, that's 2. And I need 1 for the NOT, that's 3. So I have 3 different chips on that board to design this. Where this one says what? All you need is 1 wire to replace them all. A wire, not a chip. You just take Z, your input, and you attach it, and that's your function. We'll call this function F. So instead of having, I need to get out of this and resume. Instead of having 3 chips on that board, I can replace that with 1 wire. Any other questions?
Did you do 4? I mean, not 4, 5, I'm sorry. 5B?
Using truth table, which expression each, determine using truth table which expression each of the groups are equal. So you got to find you got to do all 3 of them here, and I'll do the quick way of doing it here. I won't go each one. So that's 5B. Here we go. I have F equals A bar C bar plus BC plus AB bar. G equals B bar C bar plus A bar C bar plus AC, and H equals B bar C bar plus AC plus A bar B. So I have 3 inputs, A, B, and C. These are my inputs, A, B, C. And to make sure I don't dip below the line, because otherwise I'm going to start dipping below the line. Let's make sure I stay healthy here. 1, 2, 3, 4, 5, 6, 7, and that's 8. Here are my options. 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 1. 2 zeros, 2 ones. 2 zeros, 2 ones. 4 zeros, and 4 ones. I can do F in one shot instead of doing each piece and order them together. That'll take me too long. Let me do F here. F is going to be a 1. Let's look at it. When A is 0 and C is 0, that's an AND gate. When this is 0 and 0, when you complement them, what are you going to have? 1 and 1? What's 1 and 1 is 1. So look for A is 0 and C is 0, and that's when you're going to have a 1. This is one place. This is another place. A is 0, C is 0. That's the only place A is 0 and C is 0. I will have a 1. Or add to that. When B is 1 and C is 1. Let's find out where B is 1 and C is 1. That looks like right here and right here. Or add to it one more. When A is 1 and B is 0. A is 1, B is 0. This is A is 1, B is 0. The rest of them will be zeros. That's what F is. Let me look at G. I'll put the G here and see if they are equal. G is going to be a value of 1 when what? B is 0, C is 0. That's the only places so far. Or when A is 0 and C is 0. A is 0, C is 0. That's the same one, right? So I already have a 1. A is 0, C is 0. That's this one. It looks like that's it. And the last one, when A is 1, C is 1. A is 1, C is 1, that's this one. A is 1, C is 1, that's this one. The rest of them are zeros. Almost had it with the exception of what? This one. See this one, that's 0, 1. So they are not equal. Let me try the H. H is going to be a 1 when B is 0, C is 0. B is 0, C is 0. B is 0, C is 0, right here. Next one, A is 1, C is 1. A is 1, C is 1. A is 1, C is 1. And the last one, when A is 0 and B is 1. A is 0, B is 1. What do you notice? Are these guys equal?
F and H are equal.
F equals to H. That's a little bit faster and quicker. Instead of doing each piece, do one gate for this, one gate for this, one gate and order them. I do them that way. Cleaner and faster.
So is that, it's not equal because there's one that's different, correct?
F and H are equal.
F and H are equal.
Yep. G is not. You get that 0 here, supposed to be 1 to be equal. So everything was fine except that location. That's where G is different.
I also had trouble on 8F.
8F. Let's see, what's 8F?
Boolean algebra again.
Boolean. I'll save that paper, the graph paper. And I'll use a normal paper for that. Oh, I almost wrote on the glass. Let's add some color here. 8F. Boolean algebra.
You're out for TV.
X bar, Y bar, Z bar, plus X bar, Y bar Z, plus X bar, Y Z, plus X, Y, Z, plus X, Y, Z bar. The first thing I grabbed my eyes, these two, when I was looking at it. Look at these two. Okay. I can look at them and say, what do they have in common? X bar, Y bar. What's left? Z bar plus Z. What's Z bar plus Z? 1. These also another two grab my attention. What do they have in common? YZ. What's X bar plus X? That's YZ. Now looking at that one, X, Y, Z bar, like, too bad I don't have another one. Because if I had another one here, let me just put another one. If I had another one here, let's say I had the, oh, not Z bar, Z. If I had a Z here, what could I do?
I think it's simplified to
X,
XY.
Y, Z bar plus Z, which is what? X, Y. But I didn't have it. I have it here. I can write it twice. What's an OR gate, X plus X, or X or X? When you have an OR gate, it says X or X, the result is X. So if you have an X, you can write it twice if you want to. Well, this is just writing this input twice. So if you write it twice, you can shrink that one instead of having 3 variables now to 2 variables. Now I look around to see anything common. Can I simplify any more? No. Now let's count to see initially what we had. We had 1, 2, 3, 4, 5. 5 3 input gates. That's 2 chips. 2. We have 1, 2, 3, 4, 5. I don't have a 5 input OR gate. So I'm going to have to use 2 4s or 2 3s, whatever. So there goes another OR gate. 1 chip. That's 3 chip and the NOT. That will knock it down to another one. Now my design will be shrunk to 2 inputs here. That's 1 chip of the OR gates, 1 chip of the AND gate, and 1 NOT gate. So my design now is shrunk to X, complement that, Y, complement that, AND it together, Y and Z AND it together, and X and Z AND it together. And that's my new design, to simplify that. Where initially it was a mess. If I do the initial design, 3 input, 3 input, 3 input, 3 input, 3 input, 5 of these instead of 3. 5 3 inputs. You gotta connect every one of them. Every wire has to be connected. So you gotta pay somebody to sit there and solder them. Click, click, cut the wire, connected there. Bigger board. Nobody wants these big computers. We all want the cute little ones. You know? You see a big box, you go, look at that machine. You're making fun of them now. A computer about this big and this wide. You can replace it with something that small. Go, oh, look at this. That replaces that. So that's that problem.
So you can also do that one with the factoring, like the first 3 terms.
First 3?
Yeah.
What would you factor there?
An X bar,
Yeah, then you have Y bar, Z bar.
and then like you took out the Y bar or you took out the Z. Like you did that, and then like you factored again using one of the other.
Well, you can factor X bar and Z out of it. Oh, no, can't factor Z. Out of the 3, the first 3 he's talking about?
Yeah, so you factor on an X bar, and then.
Let me see where David's going with this. Let me see. Let me write it down, David, and see where you're going with it. Dave said, let's look at the first 3. Take X up, X bar out. So we have what? Y bar, Z bar, plus Y bar, Z, plus YZ.
So then inside the parentheses, you can take out the Z.
Out of these 2? Yeah, you can do that. Z out of these 2. You end up with Y bar plus Y, which is a 1. He said, this is a 1, right? So it'll be Z. Now we have a rule that says if you have A plus A bar B, can be written as A plus B. So if you look at that, no, I know. Well, that's just a rule there. So he's looking at this as A. He's looking at this as B, A bar. And he's looking at this as B. So applying that rule, David said, I can write that, what's inside that, as A plus B, which means Z plus Y bar. Distribute that, X bar Z plus X bar Y bar. You can do that. And now go to these 2 here and factor X, Y out. What's left? Z bar plus Z, which is a 1. So come back and add that answer down here. Notice he has a different answer than mine, but it's the same number of gates. And by the way, that's common. You'll see that soon enough when we show you a different way of doing it. You get to a point, I can take this with this, or I can take this with that. Which way you want to go? It doesn't really matter. It's up to you. I can go this way, I can go that way. And if you go this way, your answer looks different than if you go that way, but still the same number of gates. But that's one of the rules, actually, A plus A bar B. And the same thing if you have A bar plus AB. That can be written as A bar plus B. So if this is the bar and that's not, where if this is not and this is the bar. So both cases are fine. So A plus A bar B is equal to A plus B, or A bar plus AB is equal A bar plus B. Yeah.
So it doesn't matter if the other one has a bar or not, it's just a different variable, correct?
Yep, I'm just using just the rule, trying to equate them, set this equal to that. I don't care if that is,
Would be
So those-
just equivalent to say
This
A
is-
bar, B bar equals A plus B.
correct,
Bar.
yep. So I'm looking at this, I'm going, that's the complement of this, and whatever that is, doesn't matter if it's Y or Y bar. If this is Y, my answer will be Z plus Y. If this is Y bar, will be Z plus Y bar.
Okay.
So I'm just trying to match them to that rule. This is my A, this is my A bar, and this is my B. I don't care what these guys are. But that's what David decided to approach it, which is fine.
So that or thing, like, you can keep adding as much or.
You can add as many gates you want, as long as one of those gates, as long as one of those terms. So you can add as many of these. So you know what? I'm going to put another one of these here. Now, if you put X, Y, Z bar for the last one, it'd be silly, because nothing will simplify, right? But if I pick this with it, oh, wait a minute, I can cancel the Z's. So as long as you're adding one of these gates to it, one of these terms, then you're fine.